So in previous videos, we discussed linear algebra. And in this video, we start studying differential equations as the second part of the course. We will begin with the study of the first and then second order linear homogeneous differential equations with constant coefficients. So these are very special and the most elementary subclass of the differential equations. So what is a differential equation? Well, an equation involving a function and its derivatives. So that's very simple. And often we're interested in solving for the unknown function. So we need to find what it is, what is this function which satisfies this differential equation. How do these equations arise? Well, let me give you some examples. Say one has a real-world system. In its state at some given time, it's modeled by a function. Say it's a vector-valued function x of t, something that we're very familiar with from the linear algebra course. We can reason intuitively or scientifically about the rules governing the evolution of the system. In other words, we can discuss how it's changing with time in terms of current state and as a function of time. And that's the differential equation. In fact, the vast majority of models in sciences, all kinds of sciences, physics, biology, etc., they can be formulated in this form via the differential equation. Well, let's talk about population as a first example. Suppose you have a population of some kind, and the member of each member of this population behaves identically for simplicity. Then we can discuss the rate of change of the population, whatever it is, say rabbits or bacteria in petri dish. Now, the rate must be proportional to the population itself. So the rate of change, right? So the derivative of this function y, so let's say y of t, gives us the population in some units, say number of species or like number of animals of each species. Derivative with respect to time is equal to some coefficient k multiplied by y of t. So the rate of change is proportional to the function itself. So, and again, it can be anything, so peoples or animals, in which case we are talking about the population growth in the usual sense. Growth or decline, so that will depend on the sign of constant k. But then we can apply the same equation to physics, right, to the population or concentration of radioactive atoms. And if we're talking about the radioactive decay, or population of invested dollars in your bank account. And then we're talking about interest. Another physics example, so that comes with the Newton's law of motion, F equals ma, but now we're going to write it using derivatives, right? So this asserts that the path y of t of an object of mass m, so say y is the y coordinate of this point mass m, and if it's subject to force F, then we can write this equation. So force is equal to the mass multiplied by the second derivative of y with respect to time, which, as we know from physics course, is the acceleration of this point particle. Implicit in this formula, there is an assertion that the force may depend on t, y of t, and y prime of t, but it actually only depends on second derivative of t. Well, it's not really known. Why is this the case? I mean, okay, we have physics law. We understand what F equals ma is, but we don't really fully understand why it is like that. Nobody understands. Just as a joke, in all the history of the humans before the Newton, no one came up with this law, and many very smart people came up with other incorrect laws. Yeah, so this is how the world works. So, you know, he spent a lot of time pondering under the apple tree, and then, you know, he got hit by an apple, which is, you know, allegedly encouraged him to think about the laws of motion. Another example from physics, gravity near Earth. So any object is subject to the force of gravity exerted by other objects. So again, according to Newton, so this force has the following strength, like the absolute value of the force is equal to this product of the Newton's constant, capital G, multiplied by the product of masses, m1, m2, divided by the r squared. So if we have two mass m1 and mass m2, which are which are separated at distance r from each other, so this is the magnitude of the force, and we know that it's an attractive force, right? So it acts towards the other body. Now, if one of the masses is Earth, right, so near the Earth's gravity, this coefficient here, well, without the minus sign, there's a typo, g Newton times mass of force divided by the radius of the Earth's radius squared is about 9.8 meters per second squared. In metric units, right, and in feet per second, it will be about 30. Yeah, so I mean, it's you can think of the negative. If you put a vector, you can have a negative sign with the downward direction. So there's any other object subject to other forces would move according to the differential equation. Gm is equal to my second derivative of y, or just if you cancel off m because you know that it's not equal to 0, that g is equal to the second derivative of y. Right, so the acceleration of this particle is equal to this constant g. Okay, another example, springs, right? So the Hooke's law. So the stretching of the springs, stretching or compression of those springs by some distance exerts a restorative force in opposite direction, right? Which is proportional to the stretching. So if you stretch it, the spring wants to come back. If you compress it, it wants to expand. And here is the differential equation that governs this dynamics. So an object of mass m attached to the spring, say a weight, obeys the law my second derivative is equal to negative ky. So then the minus sign reflects the fact that the force is applied in the opposite direction for some constant k. And then the k depends on the internal structure of the spring, right? It's the stiffness, like, or how stiff, how robust the spring is. Now let's talk about fire and heat. The heat equation. The temperature in an object can vary over time, and it can be recorded as a function in space and time variables. So say you have a temperature distribution function t in a three-dimensional space with coordinates x, y, and z, and as a function of time t. Now, the laws of thermodynamics, which is a branch of physics that studies heat phenomena, states that all things being equal, the temperature wants to equalize, right? So unless there's no sources, external sources or sinks where the heat can leave, the temperature wants to equalize unless nothing fancy happens. So for instance, the temperature at a given point will change according to how different the temperature at nearby point is. So, and that's what this, that's how we can express the statement quantitatively, right? So the derivative of t with respect to the temperature function with respect to time. So don't worry about those del's. So those are partial derivatives. We'll introduce them. So the partial derivative, right? Partial derivatives of t with respect to time is proportional to the second derivative, to the sum of second derivatives of t of the temperature with respect to coordinates x, y, and z. We'll spend a significant amount of time discussing heat equations later. So far, let's just look at those examples. Another example, wave dynamics, wave equation. right now in Tokyo Olympics, there are surfing competitions, so you could see those waves. The surfers catch them and float, and surf. Although I must admit that the water is not as transparent as in this picture. So imagine a substance which has some preferred density, and everywhere locally responds to compression or expansion by exerting a force in the opposite direction to kind of equalize the dynamics. So, and that's just about, it happens just about in any medium. Water, glue, air, some density, and so on. So by pretending that this is an infinite collection of springs, kinda, right? So sort of think of a substance like, molecules, whatever, in a substance connected by infinite collection of springs, little springs with some stiffness K. Although physically, of course, this model is not quite precise, but it works to some extent in certain approximation. So if this is the case, it is possible to show that these, like the mass density function, right? So the mass in the unit volume, U, obeys a similar differential equation, partial differential equation, as the temperature in the previous example. Although here we have a second derivative with respect to time. So its second derivative of U with respect to time is proportional to the sum of second derivatives of U with respect to X, Y, and Z. And as we'll discuss later, this is also denoted as Laplacian of Y. So it's a second order differential operator applied to U. Okay, next, electrodynamics, Maxwell's equations. So there will be a lot of physics today. I hope it will align with many of you who also takes physics classes. So everywhere in space and time, we have permeated, so time is permeated by electric and magnetic fields, which are denoted with vectors A, E, and B, which interact with each other, and also electric and magnetic charges. These are the famous Maxwell's equations. So here this is the so-called divergence of E, right? It's the it's a scalar. Think of it as the dot product of the gradient vector and the electric field, right? It's equal to the charge density of the charges. And in this case, you see those equations are written in so-called in the SI system, where the coefficients, these constants epsilon 0 and mu 0. Some of you probably know that in CGS system, those coefficients are equal to 1, and equations look a bit simpler. Right. Second equation shows you that there are no magnetic charges, right? So divergence of the magnetic field is equal to 0. And then two other equations, they show you the curl of these two fields, right? So the third equation is the magnetic induction, right? So it's the curl of E is equal to with a negative sign, the derivative of the magnetic field over time. So the change in time of the magnetic field causes the curl in electric field, and the curl in electric field gives you this sort of this symmetric. There's this d over dt plus j, where j is so-called displacement current. Well, it's not part of the course, obviously, but of course, we should. If you are one of the physics majors and taking those classes, you will definitely work with these equations in more detail later. Okay, and then, but so as you can see here, these equations are linear in E and B. And we can still treat those equations by methods that we can develop. Okay, so this is the black hole over here, sort of artist's rendering of a black hole, which sucks up the material from the neighboring star. It actually happens in right now. Well, I mean, it happens in the universe. There are many systems like this, but not many, but astronomers know some of them. And the dynamics of this phenomenon is governed by Einstein's equations. So, as you know, Newton's gravity is only applicable at some at small distances, right? Because at bigger distances, you need to take into account that things move, right? And then once galaxy or whatever moves around, its gravitational field changes, and then you need to take into account the time it takes for the gravity signal, like for gravity to propagate from one point to another. And if everything moves, that it matters, like the relative velocities of those objects, they matter a lot. And then also when objects are very heavy, like in the case of black holes and neutron stars, you have to use Einstein's equations. So in this case, there's this function which takes values in matrices. It's called metric G. It depends on on coordinates in time. And you probably heard then that in relativity theory, time and coordinates, that they're treated on equal footing. So in a sense, you can think of this as a x, y, z, and t as coordinates in a four-dimensional space, which has negative signature. So it's this Einstein, it's so-called Minkowski space-time, and it's a matrix. So it kind of tells you how close the objects are to each other as you in space, like at different locations. This metric is different, and the metric is used to measure distances between points in space-time. Now, and the fact that this notion of a distance, which we calculate using metric, varies depending on where we look. It sort of says the fact that this space-time is curved. And then the curvatures are recorded as derivatives of the metric with respect to coordinates and with respect to time. So in differential geometry, which is a more advanced course than this one, so there's you'll take it later in grad school if you go there. Well, there's also an undergrad version. So these are called the scalar curvature R of G and the Ricci curvature Ricci of G. And while there's an equation, so obviously it goes beyond the scope of this course, all the details of how to explain it, but in a nutshell, so there's a on the left-hand side, there's a it's a tensor, right? So think of it as a matrix. So the tensors, it's basically matrix which depends on coordinates, which transforms in a certain way when you make changes of those coordinates. So there's some expression which depends on metric on the left, and on the right you have the stress energy or energy momentum tensor T, which is called over here, which records all the information about masses, energies, etc., and where they are at each point. It also depends on the metric, right? So like it's not just T, it's T with some indices, and because they're indices, it actually knows that there's a metric involved. But roughly speaking, which is sort of not quite precise, the geometry on the left is equals to the sort of mass energy on the right. But again, it's more complicated. They are coupled to each other. So, but there's a bummer here. So this is a highly nonlinear partial differential equation, right? So here this R of G is some complicated function of G, and you multiply it by G itself. So this is nonlinear already right there. This is also, this tensor is also nonlinear. So yeah, so that goes like way beyond the scope of this course. But yeah, it's a subject of differential geometry. Okay, so let's be a little bit more specific, talk about first order differential equations. So in general, so you can have, so similar to linear systems of linear equations, we'll be talking about homogeneous and inhomogeneous equations. So this is the homogeneous first order differential equation. There's a derivative of dy over dt multiplied by a of t. So in principle, it can be a function plus b of t multiplied by y equals 0. That's the homogeneous equation. Now, And to solve it, we simply need to rearrange this into this form, right? I'm sure you're familiar with this gymnastics of differentials. Like you can write this formula as dy divided by y is equal to negative b of t divided by a of t times dt, and then you integrate, right? So on the left we have log y, and on the right we have this integral, which is whatever it is. You can, maybe it's doable, maybe not, but you can formally write it as an integral, and then if you exponentiate both parts, this will be the equation. Of course, there's a constant of integration here, which will appear as a factor in front of the exponential. We'll talk about those constants a bit later. So, in particular, if those coefficients are constants, a of b, a of t, and b of t are constant functions, then this is the equation, and integration gives us this exponential function. So the constant c, right, is this undetermined constant of integration, and in exponential you have a linear function, which is just direct proportionality, right? It's negative b of a times t. So you can even, if you plug in t is equal to 0, we'll see immediately that the value of this constant is equal to function y evaluated at t is equal to 0. So there are two different problems which we'll be discussing. General solution versus the initial value problem. So given a differential equation, for example, y prime plus y is equal to 0, we can ask different kind of questions. So first we can ask for all functions which satisfy the differential equation. In this case, we want to talk about the general solution, which in this example is if you simply plug in a equals 1 and b equals 1, right? You'll get you'll get y is equal to c times e to the negative t for an arbitrary constant c. So general solution depends on this arbitrary constant. Or we can have in mind some different initial data, right? So for example, we know, right, say, the population, like whatever the value of, any physics problem that I illustrated before. So the value of y at t equals 0 is equal to 5. And this is called the initial value problem for this equation. Initial because it's, well, here it's evaluated at some fixed value of t, often at t is equal to 0, but it doesn't have to be 0. And in this case, solution is equal to 5 times e to the negative t. So this arbitrary constant is actually replaced by a value, right? So this equation does not have any more free parameters. Let's talk about existence and uniqueness. Given a differential equation, there are two basic questions. First, do solutions exist? And second, how many solutions are there? First, let's talk about existence. So if you're modeling some system by a differential equation, then since the system behaves, after all, in some way over time, it had better be the case that the solution exists, right? So for example, you start your physics experiment, you have some sets of data, initial values of all your parameters, and then you let it run, you let it evolve, and then, well, there's a hope that in the future, as the experiment progresses, you would still be able to measure the same functions, right? And then describe the whole process by some maybe complicated differential equation. Moreover, it may happen that the solutions are defined only over some time interval, right? So that's also possible. So this necessarily means that the model does not make sense after this time t, and we should be somewhat worried about times near t. So yeah, existence is, we believe that it exists. Uniqueness, okay, so maybe I'm modeling some system, then we have observed that it obeys some differential equation, like population or nuclear decay. And now you want to know how much data about it you need to measure in the beginning in order to predict its future behavior. So the space of all possible solutions of the equation, we need to, out of the space, we need to pick out one solution. So in this setting of linear differential equations, the solution space will always be a vector space, and generally a finite dimensional vector space. Thus, in order to specify which solutions we have now, we need to name a vector in the space, which we can do by choosing an isomorphism to Rn, to the n-dimensional Euclidean space. And that's already part of the story that we know. We talked about this in the linear algebra portion of the class. Often, so for instance, in the context of the initial value problems, this isomorphism between the solutions of differential equation and Rn takes the following form. So we take a function and then we map it to this vector here whose components are the derivatives of the function at some point, say t is equal to 0. So for first order equations, we take f goes to f of 0. And now, so for the second order differential equations, we go f goes to f of 0, f prime of 0, and so on. So various derivatives, first derivative, second derivative, etc., n minus first derivative, they kind of naturally associated with the coordinates in the n-dimensional space. Okay, so now let's talk a bit more about the solutions. So consider the equation ay double prime plus by prime plus cy is equal to 0. So what can we say about the space of solutions before trying to find any? So one of the solutions, for example, actually is like y is equal to 0, right? You can see that it satisfies this equation. So remember, so far we're talking about homogeneous equations. There's 0 on the right. Well, so linearity, right? Because the solution is from a vector space. Since derivative is a linear operation, if y of t and z of t are solutions, then if you plug in instead of y in a differential equation, the linear combination of y and z with some coefficients m and n, we'll get this. So this way, a times y of t plus b times z of t would also be a solution. Okay, so how many solutions do we expect, say, in this equation for this equation? So let's solve it for express it y double prime like this, and then there's a typo, there's a minus sign in front of 1 over a. So if y is a solution to this differential equation, then knowing the value of y and its first derivative y prime, so see, because essentially what this equation is saying is that the second derivative of y is a linear combination, right, of the first derivative of y and the function y itself. Yeah, so in other words, that these three elements, right, so they're linearly dependent, right? So y prime, and y double prime. So if you take another derivative from both sides of these equations, so y triple prime is equal to, again, there's a minus sign, 1 over a by double prime plus cy prime of t. We can see that the third derivative can be written in terms of the first and second derivatives, and which in turn can be written in terms of the derivative and the value of the function itself, right? Because we know how to, we can sort of substitute it back, right? Instead of y double prime, you can substitute the expression from the previous slide. And then after you combine things together, you'll get this formula, right? So b squared plus ac divided by squared times y prime plus bc of a squared times y of t. And then you can keep going, right? You can continue iterating so that we can recover all derivatives, all higher derivatives in t from just the function and this first derivative. So to put it differently, for a fixed number t0, solutions of this differential equation, we can pose a map from the space of solutions of this differential equation into Rn plus 1, right, such that f goes into this vector here, f of t0 plus f prime of t0 plus and so on plus nth derivative of t0. So image of this map has the dimension at most 2, right? Because all other derivatives are dependent, linearly dependent on the first two, on the function and the first derivative. So in other words, whatever the dimension of the space of solutions, the dimension of the space of their Taylor expansions around a given point is at most 2. So how many solutions are there actually? So this is not actually an argument that the space of solutions is two-dimensional, right? Simply because there exist infinitely many differentiable functions Taylor series expansion of which vanishes but are nonetheless non-zero. So here's this famous function, which sort of gives a counterexample. So it's a piecewise function. So for, say, when x is equal to 0, it's equal to 0. And when x is not equal to 0, or say x is, yeah, so x is not equal to 0, it's exponential to the -1 over x squared. So if you haven't seen this function before, try to plot it at home and see what it does until it's an interesting function. And then you can check that the if you formally use the Taylor series, you formally compute all the coefficients of the Taylor series, derivatives of this function, and evaluate it at x equals to 0, right? You will get that the Taylor series is 0, but the function is not. It has a non-trivial profile, right? Because it has this exponential behavior. However, in fact, there are at most 2 solutions to a linear second order ODE. So ODE stands ordinary differential equation. So this fact is true, that the space of solutions is two-dimensional, but it's not because what we said in the previous slide. And in fact, it's a special case of a general uniqueness theorem. And we'll prove it later in the following videos. Let's talk a bit more about finding the solutions. Take the equation, second order equation, y double prime plus by plus cy is equal to 0. So exponential functions worked for solving the first order equation, and we can try those here. Maybe they will work as well. Well, some people who like this terminology say it's exponential ansatz. It's a German word, right? It should be spelled with capital A. So suppose y is equal to r times t, where r is a constant. So when is this 0, right? A y prime plus by, y double prime plus by prime plus cy is equal to 0. Well, let's just plug in, right? So we know how to differentiate exponential. So we get this exponential multiplied by the quadratic polynomial in R. Well, since exponential is never equal to 0, we know that this function is a solution if and only if this quadratic polynomial AR squared plus BR plus C is equal to 0. So this is called the auxiliary equation to this differential equation. So it's a polynomial equation which is auxiliary to the differential equation. Well, we know that quadratic equation in general has 2 solutions. And this is the infamous formula from high school, from middle school. And So whatever they are, right, we can find the solutions e to the r plus t and e to the r minus t. And then since these equations are linear, then any linear combination of this form, constant a multiplied by e to the r plus t plus constant b multiplied by e to the r minus t, is again a solution. So we have a two-dimensional solution, space of solutions, and therefore it must be all the solutions. Well, and then some interesting things happen unless those two roots of the quadratic equation coincide. So what if r plus is equal to r minus, or what if those roots are complex, right? So if the discriminant of this quadratic equation is negative, we will have complex roots. Well, recall that the functions e to the at for different a's, different type of a's are linearly independent because, well, the eigenvectors of d over dt with different eigenvalues, right? So you cannot make them linearly dependent. So we have found that there are three possibilities here, right? So the discriminant is positive, and then numbers r plus and r minus are real and distinct. And the space of solution is spanned by these two functions, e to the r plus t and e to the r minus t. Then if the discriminant vanishes, then r plus is equal to r minus, and a one-dimensional space of solutions, we have just one-dimensional space of solutions because these two functions just coincide, they are the same. Well, maybe there are other solutions. And if the discriminant is negative, then those numbers are complex. So and then there are solutions, the e to the r plus minus t are also solutions, but in a formal sense, right? So they still formally satisfy the differential equation. Of course, if you consider everything over complex numbers, then it's okay. Then there is no problem. But still, we can ask ourselves, can we find a real solution? Is there any way to write down a real solution? After all, everything was real in the beginning, right? So the differential equations was real. Functions takes real values initially, right? The coefficients were real, so we should be able to find the real solution. Okay, so first let's consider the second option. And since the first option is done, now let's consider the case when the discriminant of the auxiliary equation vanishes. So r plus is equal to r minus. So see what happens. Let's sort of try to approach this case as a limit from the first case, right? When we have two different solutions which are linearly independent, e to the r plus t and e to the r minus t, as r plus minus r minus approaches 0. Or we can relabel them like this. So e to the rt and e to the r plus epsilon t, and set epsilon to 0 and see what happens. So let's consider this function here. 1 over epsilon multiplied by the difference of those exponentials. Well, using rules of calculus, we can calculate this limit, which is more or less the derivative by definition. And that's equal to t times rt. Right, so dependence on t pops out in front of the exponential. More generally, in a sense, we will which is sort of at this moment not going to be precise, right? So that this map from the span of these two vectors into the span of these two vectors, we can set up such map, right? So while this above argument could be made into rigorous mathematics, it's much easier to just check, right? So you can simply check that these two functions are indeed solutions of this equation, in case when the roots of the auxiliary polynomial are coincident. So consider this function t times e to the rt when r is this coincident root, take a derivative, right? Then take a second derivative, and just plug it back into the original equation. Well, after careful reordering the terms, you'll get quadratic polynomial times t e to the rt plus 2ar plus b, which, as you can see, is the derivative of this auxiliary polynomial. So in order for this to be a solution, we should have this thing to be satisfied. Now, by assumption, this is already equal to 0, right? So that was our characteristic polynomial, auxiliary polynomial. And since b squared was equal to 4ac, so if you look above here, this is the case that we're studying, r is equal to just negative b over 2a. And also we have 2ar, so therefore the second parenthesis also vanishes. So this is satisfied, and this is indeed the solution. So everything is consistent. So let's summarize. There are three possibilities. Positive discriminant, the space of solutions is spanned by these two functions. Coincident roots, then the space of solutions is spanned by exponential of negative b over 2a and t times exponential with the negative b over 2a, t. And the negative discriminant, that we have this formal solution of the differential equation, but we still need to find the real solution. So let's talk about this third case, complex roots. Now, so as we discussed, as we just mentioned, these are solutions of the equation. However, if you want a real valued solution, this will not fly, right? We need to do some extra work. So what if we take the real and imaginary parts of those solutions? So in order to this equation to be satisfied, both real and imaginary parts must vanish. Right, so here's a simple calculation with trigonometry, right, of the complex exponentials. Since the exponential to this thing is equal to this expression, right, so this is the solution of the quadratic equation, right? We know that discriminant is negative, so we can rewrite it as, can single out I, right, and then now the expression in the under the square root is positive, right? And then we just using the formula of calculus, write it as cosine of this function plus minus I times sine of this function, and everything multiplies by this real valued exponential e to the negative b over 2a times t. And so clearly, this first expression with the cosine will be the real part, and the second expression with the sine function will be the imaginary part. So as a quick sanity check, let's look at the case when b is equal to 0 and a and c is equal to 1. Right, so you have this equation, y prime prime plus y is equal to 0. Then the formula from the previous slide, you can substitute. So this formula here gives us simply cosine t and sine t. Right, so there is no exponential because b is equal to 0. And probably this is the one of the equations that you saw in solutions for oscillator, which we'll discuss in the following videos.